Welcome back to Larry's Classroom. We will continue our study of electronics with the discussion of Ohm's law. Ohm's law to solve for current is equal I equals V over R, or current I is equal to V divided by R. And the fraction bar and the divide sign have basically the same meaning in mathematics. Now we're going to draw a little circuit here to illustrate how this here equation works. Now we've drawn a multiple battery pack that we can tap off different mounts. 2 volts, 4 volts, 6 volts, 8 volts, and 10. 2 volts, 4 volts, 6, 10 volts, and 12 volts. We'll put an amp meter in here. Amp meter. We're going to have a tappable switch so we can connect any of those points. We're going to draw a resistor. This resistor is a 2 ohm resistor. Using this formula, I equals V over R, or V divided by R. If we're set here, we have 2 volts. And we have 2 ohms. So we can calculate, using this Ohm's law, the relationship between voltage, current, resistance to be 1 amp. We'll go to the next position. 4 volts. If we move the tap up 1, 2 ohms. That would allow us to calculate that we had 2 amps. We'll just use the big A to symbolize amps. Or ampere. The next position, the 6 volt position, we would have 6 volts divided by 2 ohms. That would give us 3 amperes. The next position, 8 volts divided by 2 ohms would give us 4 amperes. The next position, 10 volts divided by 2 ohms would give us 5 amperes. And in the final position, we move it all the way up to the 12 volt tap. We would have 12 volts divided by 2 ohms, and that would give us 6 amps. Now in this case, we are given the resistance, and we have an adjustable power supply. In a real circuit, we might have to take voltage measurements or current measurements or resistance measurements to come up with these things. But what we've shown here, as we increase the voltage, the current increased. We have 2 volts, we went to 4 volts, 1 amp, went to 2 amps. So we doubled the voltage, we doubled the current. Go from 4 volts down to 8 volts, we double the voltage again. We go from 2 amps to 4 amps. We have doubled the current again. So as we double the voltage, we double the current. So basically what that says is that current and voltage are directly proportional. If we increase voltage, we increase current. We're going to do a few other examples here. We're going to draw another little circuit here. Got a battery here. We're not going to put the amp meter in, we're just going to do some calculating. It's possible to have high voltage and low current. If this was 1,000 volts, and this was 1 million ohms, or we could call it 1 megohm also, 1 megohm, million ohms, we would have 1,000 volts. The current would be equal to 1,000 volts divided by 1 million ohms. This formula here, I, voltage divided by resistance, I, voltage divided by resistance. And that would give us a current of 0.001 amps, which we might also call 1 milliamp. Milli meaning 1,000, and this is 1,000ths of an amp. So here we see that we can have a high voltage and still have a low current if we have a very high resistance. But we can also have a low voltage, 10 volts, and of even lower resistance, 0.01 ohms, or 100th of an ohm, using the same Ohm's law, to solve for I, voltage over resistance. So we have 10 volts over 0.01 ohms, and we come up with 1,000 amps. So here we have an example that shows that we do not necessarily have to have a high voltage to get a high amperage. We had not a very high voltage, 10 volts. We had a very low resistance, 100th of an ohm, and we ended up with that 10 volt, not very high voltage supply, providing 1,000 amps of current flow. We're going to do another example. Let's say this is a heater, which is a 10 ohm heater resistance. Maybe it's the resistance element in your toaster or something. And we have 120 volts supplied there. Again, by using this formula, I current equals voltage divided by resistance. We have 120 volts divided by 10 ohms. This leaves us with 12 amps, or amperes. So we have here a more middle of the road voltage, quite a bit more than 10, but a lot less than 1,000, and a more middle of the road resistance, was quite a bit less than 1 million, but a lot more than 100th. So we have a kind of a medium range voltage, and a medium range resistance, and a medium range amperage. 120 volts, 10 ohms, 12 amps. We're going to do one more example of this type. Say this represents the resistance of the element of a fairly small light bulb. Again, we have 120 volts here, but this resistance here is 3,000 ohms. Same formula, I equals voltage divided by resistance. Hit another equal sign. We're going to put the values in here. 120 volts, 3,000 ohms, and we end up with 0.040 amps, which you can see that's like 40 thousandths of an amp, which we can also write that as 40 milliamps. The thousandths gives a little M per milli, just like the big M gives a million when we talked about megohms. But this shows that we can have medium current, pretty high resistance, very low voltage, a very low current, medium voltage, fairly high resistance, a fairly low current in the milliamp range, thousands of amps. So we've seen that high voltage doesn't necessarily mean high current. High voltage with a high enough resistance can give you a fairly low current. We've seen that low voltage does not necessarily mean low current. Low voltage within low enough resistance can give you low current. And we've seen some medium range examples. Now we're going to start with this here. I'm going to put that formula back up there. Current equals voltage divided by resistance. And we're going to solve that for V. I, current, equals voltage divided by resistance. We want to get this V, or voltage, alone. So we want to get rid of this resistance on this side. So this is resistance on the bottom of the fraction, or the denominator, so we'll multiply it times R. We'll multiply this times R. I'm going to put a little cross here, so these will cancel, leaving R cross, all R multiplied by I equals voltage. And now we're going to write this in a little bit. We'd like to get the V on the left. It's an equation. We can just swap it over. So we can say that voltage is equal to, and now this is multiplication, so we can change that order without a problem either. I times R, which we often write as voltage equals IR. In algebra, when you put two variables close together with no symbol, that indicates multiplication. So we've determined that this here equation that we started with to solve for I can be modified with basic algebra to solve for V, for voltage. So we're going to put that up here. We're going to say that voltage equals IR. Now we'd also like to be able to solve for R. Let's take this guy right here, which we got by transposing this by multiplying both sides times R. So we're going to say voltage equals I times R. We want to get the R alone to solve for resistance. We're going to divide by I. Divide both sides by I. Now the i's on the top and bottom of the fraction and the numerator and denominator can cancel. So we have voltage over current equals resistance. But we like to have the resistance on the left, so we're going to change the order of this equation. R equals V over I. This equal sign, anytime you see an equal sign, that indicates equal sign, this indicates it's an equation. So we've taken this equation and we've modified it. We've solved for three different variables. R equals V over I, or V divided by I. So using simple rules of algebra, we've taken this equation, which we call Ohm's law, we started with a formula, or the equation for current given voltage and resistance, and we modified this to solve for voltage using simple algebra, and we modified again to solve for resistance. So we've got three forms. These are all Ohm's law. It's basically the same equation rearranged to solve for a different variable, and we see that current is equal to voltage divided by resistance, voltage is equal to current times resistance, and resistance is equal to voltage times current. We're going to talk a little bit about practical units. If we have 1 ampere, that's equal to 1 volt divided by 1 ohm, which you can see that that's basically this first equation. 1 amp, 1 volt divided by 1 ohm. By the same token, 1 volt is equal to 1 amp, 1 ampere times 1 ohm. So with these units, we see that we have volts equals amps times ohms, which is exactly what we have here. Volts equal current times resistance. The third way to look at this, we're using our basic units. We say that 1 ohm is equal to 1 volt divided by 1 ampere. So here we've got a third form of Ohm law using our standard units. Ohms, resistance, equals voltage divided by current. Volts divided by amps. So this one matches with that one. This guy matches with that. And this guy matches with that. So we've got these three forms of Ohm's law, and we've kind of shown how they relate with actual real values, amps, volts, and ohms. In case you don't want to do that algebra every time, we have a simple memory aid. We draw a circle, we draw a line to the top, and we put the voltage on the top. And we draw another, divide the bottom, and we put I and R, which is this voltage, resistance, and current. So this little memory aid here, if you do not want to use algebra to solve this simple equation for different variables each time, if you want to find the current, you can put your hand over that, and what does it take? Voltage divided by resistance, which here is what we had. Current equals voltage divided by resistance. If you wanted to solve for resistance, we cover up the R. Resistance would equal voltage divided by current, which is what we had here in our third form that we derived. Resistance equals voltage divided by current. Resistance equals voltage divided by current. Looking for the voltage, we cover up the voltage. Voltage equals current times resistance. Voltage equals current times resistance. So this is a handy little memory aid that you can use to avoid having to use algebra to solve for different variables each time. But I like to see that you understand how they relate. Now we have different types of units we can use. We use a little symbol like this to indicate micro. Micro, which that's equal to 10 to the minus sixth. So if we had, let's say that we had 3 microamps. Use the proper symbol, mu. Greek small lowercase Greek letter mu, I believe is what it's called. Okay, so 3 microamps. That would be equal 3 times 10 to the minus sixth amperes. So if we had 3.0 times 10 to the minus sixth, we would basically have to move, being that's a negative number, indicates move our decimal place to the left, we have to move to the left 6 places. 1, 2, 3, 4, 5, 6. We'll put a leading zero. So this 3 microamps would equal to 0.000003 amps. And you can see this makes a little more manageable unit for these small amounts of current than throwing out all of these decimal places. So micro is always going to be 10 to the minus 6. You'll see it used in a lot of places. Now we're going to put a little m, which equals milli, and that's equal to 10 to the minus third. Say we got 3 millivolts. that would be equal to 3 times 10 to the minus third volts. This minus third is the conversion from millivolts to volts. So by the same thing, we go 3.0 and we move the decimal place 3 places left now. 1, 2, 3. We get 0.0003 volts. So, I gotta wrote that down wrong. 0.003 volts. So that would be equivalent to saying 3 millivolts. So there's another way we can make smaller units be more manageable, easier to work with values. So we got micro, 10 to the minus 6, milli, 10 to the minus third, and then we got kilo. We got K, which equals 1,000, which equals 10 to the third. So if I say 4 kilovolts, 4 kilovolts, that would be 4 times 10 to the third, positive third, volts, which if we take the 4, now we got a plus value. We have to move our decimal place from here over 3 to the right. 1, 2, 3. So that becomes 4,000 volts is equal to 4 kilovolts. So that K, 1,000 times 10 to the third. And the idea of this is to give you more practical to use values. We're going to go one more. The big M, as opposed to the little m, equals mega, which is basically 10 to the 6th. So if I have 2.5 meg ohms, that will be 2.5 times 10 to the 6th ohms. And then this indicates the positive 6, and this exponent of 10 indicates power of 10, indicates to move the decimal place 6 places to the right. 2.5. I'm going to add some zeros so I can do this. 1, 2, 3, 4, 5, 6. So I want to get my decimal place over there, so I have 2, 5, 0, 0. So this 2,500,000 ohms is equal to 2.5 meg ohms. Now the idea of these little prefixes here basically allows you to work with more practical numbers. So I don't have to say 0.003 ohms, I can just say 3 0.03 amps, I can say 3 milliamps, or instead of saying 2,500,000 ohms, I can say 2.5 meg ohms, and so on. So this makes these numbers, large numbers and small numbers, to be more practical to manage. So we're going to talk a little bit about the linear proportion between voltage and current. I'm going to draw a little circuit here, and we're going to have a variable voltage supply. We're going to put an amp meter in here to measure the current. I'm just going to say AM for amp meter. Yeah, just AM for amp meter. We have a resistor here, and this resistor is going to be 2 ohms. 2 ohm resistor. And we have a variable voltage supply that goes 0 to 10 volts. So we're going to voltage, resistance, and current in amperage. So we're going to go with 0 volts, 2 volts, 4 volts, 6 volts, and 8 volts. And our resistance is going to remain 2 ohms because we're varying the resistance, or varying the voltage. And we're going to use this here formula that we call current equal voltage divided by resistance. We're going to calculate the current for each of these that we would measure on the amp meter if we had this circuit. Well, 0 volts divided by 2 ohms, 0 divided by anything is 0, so we have 0 amps. The second voltage point that we selected, 2 volts divided by 2 ohms, 2 divided by 2 gives us 1 amp. The third point that we've done, we have 4 volts divided, we still have 2 ohms, 4 volts divided by 2 ohms gives us 2 amps. The fourth point, we have 6 volts divided by 2 ohms. 6 divided by 2 gives us 3 amps. The fifth point that we chose to, I want to call it 10 volts here, don't I? Divided by 2 ohms. 8 volts divided by 2 ohms gave us 4 amps. And 10 volts divided by 2 ohms gave us 5 amps. Now we take a look at something here. We had 2 volts, 2 ohms, 1 amp. We doubled the voltage, 4 volts, 2 ohms, 2 amps. We doubled the voltage again, 4 to 8 volts. We went 2 to 4 amps. So if we double the voltage, we double the amperage. Down here at 10 volts, we have 5 amps. If we go to 2 volts, which is 1/5 of the voltage, our current went to 1/5. We had 8 volts, 4 amps. We half the voltage, go to 4 volts. We get 2 amps. So what we see here is that the voltage and the current in this type of circuit, and can be calculated by Ohm's law, vary in direct proportion. If we double voltage, we double current. If we half voltage, we half current. We're going to draw this little graph over here. We're going to put resistance on this, resistance in ohms, on the horizontal axis, and we're going to put current in amps, in amperes, on the vertical axis. So we're going to put some markings 2, 4, 6, 8, 10. So it's 2, 4, 6, 8, and 10 ohms. Excuse me, I want voltage on voltage on the horizontal axis, not ohms. And still having amps up here. And we want to go up to 5 amps. 1, 2, 3, 4, 5. So we have voltage on the horizontal axis, and we have amperage on the vertical axis. So we had 0 volts, we had 0 amps. So we plot a point right there, 0 volts, 0 amps. We had 2 volts, we had 1 amp. So we plot a point right there, 2 volts, 1 amp. We had 4 volts, we had 2 amps. 4 volts up to 2, we can plot another point right there. 6 volts, 2 amps, 2 ohms. 6 volts gave us 3 amps. So 6 up to 3, we plot another point right there. 8 volts gives 4 amps. 8 volts up to the 4, we plot another point right there. And 10 volts gave us 5 amps, so we plot another point right there. Now what do we observe here? All these plotted points lie in a straight line. And this is what we call linear. The characteristic volt amp curve of a resistor is linear. They all line up in a straight line. And that was, if we saw over here, we doubled the voltage, we doubled the current. So we keep going up at the same angle. Not everything is linear. A light bulb, say this was a light bulb, we're not going to put a value on it, but we'll draw a light bulb here as a little coil with a circle around it. And you've probably seen, I might have shown you that before, but we got a little coil. This is a schematic, one of the schematic representations of a light bulb. You might see a few others with maybe a zigzag line or something, but now a light bulb, as the current increases, the resistance changes because it gets hotter, and a hotter temperature makes the resistance increase. So if you did the voltage and current graph of a light bulb, because the resistance was increasing as the current increased and the light bulb got hotter, you would not be seeing an exact straight line. You'd see a curve that kind of rounded off like that. This is not linear, but we still see that increased voltage gives increased current. So the relationship between voltage and current is still a direct relationship. As we increase voltage, we increase current. Now we're going to think about what would happen if we had a fixed voltage here. I'm just going to put a V and some resistance which we can vary. And I'm going to draw a line through that to indicate that can be varied in resistance. This is another way we can get a variable resistor, just with a line through it. I think we talked before about a symbol like this, but we're going to show you a new symbol for variable resistance, because in this case we don't really care about tapping it off. But what would happen, we're going to use this voltage equals I times R. That's what I want. We've got a variable resistance, so we've got a fixed voltage. So what happens in this situation, as we increase the resistance, we've got a fixed voltage, we're still using this guy. This would not be straight line either. It's a curve that looks kind of like this. So as we increase the resistance, current goes down. So now we have an inverse relationship. Higher resistance gives us lesser current. Lesser resistance will give us greater current. And you can see as R got bigger and bigger and bigger, this gets smaller and smaller and smaller. So you're going to see this gets closer and closer to this zero value the further out we go. So this is what we call an inverse relationship. Higher resistance gives lesser current. Still a valid relationship, but it's not linear like we've talked about a little bit. We're going to talk about electric power now. The unit of power is a watt. And a watt was named after James Watt, who was another one of our electrical pioneers. And a watt of power equals the amount of work done in 1 second by 1 volt of potential difference in moving 1 coulomb of charge. So we're going to draw a circuit here, 1 volt PD. We're just going to draw a resistor. We don't really care what the value of it is at this point. But if we move 1 coulomb of charge from one side of that supply to this supply, which has a 1 volt potential difference, in 1 second, that is 1 watt. Watt is a rate of use of power. Another way to look at it, being a coulomb, 1 coulomb per second is equal to 1 amp, or 1 ampere. Now, then watts is equal to potential difference, voltage, times amps, amperage. So watt would be what the amount of power required to move 1 coulomb charge through a potential difference of 1 volt in 1 second. And of course the 1 volt, 1 coulomb 1 second gave us amperage, and the voltage, if we doubled the voltage, would be twice as much. So basically this says that watts, a rate of use of power, is equal to voltage times current. So we're going to say P equals power, in this case in watts. So power equals voltage times current. Now this formula can be transposed too. Let me put that right here. Power, just like we did the other Ohm's law thing, we can take this power formula divide both. If we want to solve for current, we divide both sides by V. The V's cancel, so we have P over V equals I, or we can change the order of the equation, don't matter. Power over voltage. So we have our second form of the power formula. We have the current equals power over voltage. And this is, amperage, watts, and volts, just like we've been saying all along. We'll take this thing here, I equals power. Let's take the first one. Maybe we'll take this power equals voltage times current. We want to solve this for voltage. We're going to divide both sides by current. Divide by current. The currents cancel, so we have power over current equals voltage, which we can change the order of this equation just because we're more comfortable with it that way. Voltage equals power over current. And we'll write that up here for our third power formula. Voltage equals power divided by current. My units I'm using here, power, watts, voltage, volts, and current, which we use the I for intensity, and that's in amperes. Now we can we can kind of do the same sort of a memory aid with this set of formulas that we did for Ohm's law. These are our power formulas. We can draw a circle like we did before. And we can see that our power is always on the top. And we're going to put current and voltage. So if we wanted to solve for power, we cover up the P, current times voltage. We want to solve for current, we cover up the I, power divided by voltage. We want to find voltage, we cover up the V, and we get power divided by current. So we got three ways of representing those power formulas, and we saw how we manipulated them algebraically, and we also have seen a simple little memory aid to help us remember that. I'm gonna draw this here. I'm gonna put these back up here. Power equals voltage times current. Current equals power divided by voltage, and voltage equals power divided by current. Let's just say we have a 120 volt light bulb. We'll draw a little circuit here. We'll draw a light bulb. 120 volts. And we have 1/2 amp here flowing through that. So we want to know what the power is. We're given the voltage, we're given the amperage, we want to find the power, so use that. Power equals voltage times current. So this equals 1/2 times 120, 1/2 amp times 120 volts equals 60 watts. So if we had a 120 volt supply, 120 volt light bulb, and was drawing a 1/2 amp current, we would know that that is a 60 watt light bulb. We'll give a couple more examples here. We got 120 volt light bulb. And we have, it's a 100 watt light bulb. What would be the current? Well, we want to solve for current. So we'll choose this one. I equals power divided by volts. So I would equal power, which was 100 watts divided by 120 volts. And when we did the arithmetic, we'd have about 0.83 amps. So what we're showing here, if we know the power and we know the voltage, we can solve for the amperage. I'm going to do another example with another size of light bulb. Again, it's a 120 volt light bulb, 120 volt, and it's a 40 watt light bulb. So we would basically, again, we want to find the current. Power divided by voltage. Current equals power divided by voltage. So that equals 40 watts divided by 120 volts. That's basically 1/3 amp. Or if you go to decimal, it might be 0.333 amps. So we've done a little bit of work with the power formulas and see how that, and we use a very similar method to solve for different variables in the power formula that we use to solve for different variables in Ohm's law. Work and energy are basically the same. power is the rate of work. Let's just say we have a heavy load sitting on the floor. Gravity's pulling that load down. And say it takes us 100 pounds of force to make that load move. If we move that load a distance of 5 feet, this is gravity here pushing down. That's why we have the resistance here. Gravity's still pushing. But if it took 100 pounds of force to make that load move, and we moved it 5 feet, the work we would have done would be force times distance, which would be 100 pounds times 5 feet would be 500 foot-pounds. Now, that's how much work we did moving that load. The power is related to how much fast we moved that load. If it took us 1 second, then we would have been producing energy, doing work at the rate of 500 foot-pounds per second. Feet times pounds divided by seconds. If the same load, we did the same amount of work, but it took us 2 seconds, we would be 100 times 5 is 500, so we're going to write that out. 100 times 5, 100 pounds of force times 5 feet divided by 2 seconds equals 500. 500 foot-pounds of work divided by 2 seconds. That works out to 250 foot-pounds per second. Now, we have a standard of power, 1 horsepower, 1 HP. And that is equal to a rate of doing work of 550 foot-pounds per second. So, you see, in the first case, we moved that load 5 feet that took 100 pounds of force to move. In 1 second, we were doing work at the rate of 500 foot-pounds per second. So we were doing work at slightly less than a 1 horsepower rate. And in the second case, when we moved the load slower, we did the same amount of work. We did the same 500 foot-pounds of work, but we did it in 2 seconds. So we were doing a rate at 250 foot-pounds a second, which is slightly less than 1/2 of a horsepower. When it comes to conversion factors, one horsepower is a rate of doing work which is also equal to 746 watts, again a rate of doing work, which is also equal to 550 foot-pounds per second. So basically, we have 3 ways of describing the same rate of doing work, same horsepower. 1 horsepower, 746 watts, or 550 foot-pounds per second, which can be useful if you got to make some conversions and such. And we saw that power is work over time, which is very well demonstrated by the 550 foot-pounds of work divided by the time in seconds. So, work, force times distance, how much actual energy you put out, and power is how quickly and what rate you did that work. And 1 joule is the rate of doing, is amount of work. Joule is an amount of work. Very much like foot-pounds could be the amount of work. And it's the amount of work's done if you use 1 watt for 1 second. So if let's say we had 3 watts output, power rate, and we put out that much power for 10 seconds. How much work would we do? We would do 3 times 10, we would do 30 joules of work. So work is power. Oh, this is divided. I didn't do that right, did I? Oh, that's right. Power. Yeah, this is fine. Power is work divided by time. Work is power divided by times time. We got a unit of work. You might think it's a unit of voltage, but it is not a unit of voltage. It's called the electron volt. Which we write this way, EV. The electron volt is the amount of work done to move 1 electron across the potential difference of 1 volt. So we're going to draw our battery again. We're going to call this a 1 volt potential difference, and we'll move it through some unknown resistance. If we make 1 electron, a single electron, make that path from this side of that 1 volt potential difference to the other side, we will have done 1 electron volt of work. We often use volts for potential difference, but electron volt is an amount of work. It is not a potential difference. Now if we move, what was that number? 6.25 times 10 to the 18th electrons. Instead of a single electron, we do 6.25 times 10 to the 18th electrons. We move through that 1 volt potential difference. It's going to be 6.25 times 10 to the 18th electron volts of work done. But 6.25 times 10 to the 18 electron volts of work is equal to 1 joule of work. 1 joule of work equals 6.25 times 10 to the 18th electron volts. Now you may remember that a flow of 6.25 times 10 to the 18th electrons per second was 1 amp. So basically, if being 1 joule equals 1 watt, times equals watts times seconds. If we do 1 joule of work in 1 second, so if we have 1 amp flowing here, we do 1 joule of work in 1 second. 1 amp and power equals voltage divided by current, right? Right. Power voltage times current, excuse me. Power equals voltage times current. So if we move 1 joule in 1 second across that 1 volt potential difference, that's going to require 6.25 times 10 to the 18th electrons, which we know to be 1 amp. So if we have 1 volt and 1 amp, that's 1 watt. But we see the number of joules of work will be the number of watts times the number of seconds. Here we had 1 watt, and because we had 1 amp, we had the 1 second. That gives us 1 joule. So a current flow of 1 amp across a 1 volt potential difference will do 1 joule of work in 1 second. And that's why we can say that joules of work done, let's write that down, joules of work done, spell that correctly, Joule, of work done equals the rate of doing work. The rate of doing work is watts times the number of seconds. So that's kind of how all this stuff ties in together. Now, one more thing I want to talk about before we hang it up for the day here. We're going to talk about kilowatt hours. Kilowatt hours is a total amount of work or total amount of energy, which is basically the energy flow times the time in hours. So let's say we have 120 volts of supply and we're drawing 10 amps off of that supply. Well, power equals volts times current, right? So 120 times 10 gives us 1200 watts. And back to our kilo prefix, that's the same as 1.2 kilowatts. So 2 kW, kilowatts. And if we draw that for 3 hours, and that's basically what kilowatt hours is kilowatts times hours. So if we have that 1.2 kilowatt load, and we run that load for 3 hours, that gives us an amount of energy used of 3.6 kilowatt hours. And this is basically what your power company uses to monitor your bill. They have your meter on your house spins, the speed it spins depends on how many watts or kilowatts you're drawing at any given time, and the amount of distance that it moves the meter depends on how long it spins at that speed. So 120 volts times 10 amps, one example, was 1200 watts, 1.2 kilowatts. This would be very similar to a small space heater you might plug into the wall. And the 1.2 kilowatts for 3 hours times 3 hours was a total of 3.6 kilowatt hours of energy used. And you see in all of these situations, energy use was how much power was used divided by the time. That's the rate of usage. We convert it back to total energy by taking the rate of energy use and multiply it by the time, and we convert it to a total amount of energy that way. So let's see if I can energy basically equals power times time. The amount of power you used, time you used it. Power equals energy divided by time. And you can see divide by time makes it a rate. Total energy was the rate of use times the time you used it. The power, which is basically how fast you're using energy, was the total amount of energy divided by the time. Well, we could solve this for time, but I don't really see the need to at this point. This kind of goes back to our power formula. So I'm gonna Ohm's law. I'm going to put the little ohms thing here, volts, I divided by R. So we had I equals V over R. We had V equals I times R. And we had R equal to volts divided by current. And we're going to do kind of the same thing with our power stuff here. I'm going to draw kind of a power formula. Remember, power current voltage. So current equals power divided by voltage, which we got by doing that. And we're going to say that power equals current times voltage. And we have the voltage equals power divided by current. So here's Ohm's law. And here's our power formulas. So that kind of paraphrases a lot of what we talked about with Ohm's law today. Voltage over IR, I, voltage divided by current, V, current divided by voltage, or times voltage, R, voltage divided by current. That gives the 3 Ohm's law equations. Power, current equals power divided by voltage. And the power was the current times the voltage, and the voltage was the power divided by the current. So that's probably enough for today. I'm going to say good afternoon to you all, and until the next time, But be sure to subscribe so you get notifications and such. And until the next time, keep on learning.